right, and now please allow me to introduce Dr. Joe Kiter. Dr. Kiter is a research associate working at the program of computer graphics at Cornell University. He received his PhD from the University of Pennsylvania, and his research focuses on interdisciplinary digital design of sustainable architecture. He works on advanced numeric simulations that calculate a building's daylighting behavior, thermal performance, and material properties. Dr. Kiter will be presenting on measuring Skylight for sustainable design.
Okay, thank you, everybody. I'm pretty sure everybody probably can hear me too. I want to thank Chip and the members of ASD for bringing us all together here. One thing we always talk about at lunch and every time we get together is a lot of times with these spectral applications and properties and things that we're doing, we're using a lot of the same math to attack similar problems, but coming at it from different angles. And I'm going to come at it from a totally different angle than what you saw with the soil work and with the volcano work. We're trying to show what we're doing for rendering and sustainable design. So I come from Cornell University, and at Cornell, I work with Don Greenberg, who is one of the premier members of computer graphics. And Don's lab's been working on a variety of rendering problems for the last 40 years, from this article in Scientific American to some recent rendering work we did last year. Now, the difference that Don tries to do with our lab, and it's a philosophy that I've adopted and a lot of people have adopted that have come out of our lab, is we're really concerned about what we're actually producing is correct and not just making the pretty picture for a Pixar movie or a DreamWorks movie or a Disney movie. We want to take something that we know exists and be able to perceptually validate it and physically validate it. So this was an early experiment back in 1970. Granted, it's only a box, but for 1970, this was a big deal to actually validate something. Nowadays, obviously, we want to validate large vegetation and a lot of different movies for buildings. So Don initially set up to do his bidirectional reflectance function validation, go to a reflectometer that did things in the visible range that measured basically between 360 to 720 nanometers, that was set up with 3 degrees of freedom, so it could do things that Chip was thinking about doing when he took his measurement device out into the field of rotate the light, rotate the sample, and rotate the camera to get all these different angular dependence of light reflection for card paint, for drywall, for cloths, and all these other interesting materials. Now, we've moved on in the last 40 years to do some stuff with architecture to be a different application. And the way I pitched this is we're still doing things for computer graphics, so not just rendering a movie for Pixar, but taking those same couple wavelengths of light and moving it out of the visible and moving it into the IR so that we can do things for daylighting analyses, do things for sustainable design, to do thermal studies. So when you design a building, it actually can have some impact on what's going on. Now, sustainable design has started to become a little bit of a dirty word, I would think, because people are throwing it around way too often. So, if I just put a tree in front and then the tree goes away in the winter, I now have sunlight coming in and they're trying to say, oh, this is going to make your building better. It's very similar to the early days of computer graphics, where I can make a very pretty picture, but it doesn't mean it's radiometrically accurate at all. So, what we want to do is be able to use the knowledge of rendering and computer graphics to create buildings that can actually impact and have sort of this net zero impact on society so that you feel comfortable where you work. You're not just in an enclosed space. There's big office windows, there's daylight coming in, you feel comfortable thermally so you're not too cold or not too hot. There's micro zones inside of there, and we're moving from basically simple zoning to more of these micro zones. This is an example of a controlled environment in California where they have birds flying around, and so their own microenvironment, they use this daylighting to funnel into the area and get the properties that they want. Now, the interesting thing about this is after they built it, they had an idea of what was going to happen, and what happened in reality was totally different. This is the problem we're trying to solve, is the model that you simulate is validated such that you actually get it when you actually build it. And this is something that has not been done in the architecture field, in the computer graphics field, and something that we're trying to create. So you don't have to sort of create different fixes for it after the fact. Another fact is buildings are going to become more modular as they grow in different parts in the future, where these facades will start to be dynamic. They'll change over time and allow different daylighting in. So if you have something in Ithaca in the winter, For Rochester, it's the same problem. It's very cloudy from October to December. You know, when Don brought me up to recruit me to Ithaca, it wasn't California skies. You know, it's you know, gloomy. They don't really tell you the sun's going to disappear for 4 months of the year. We want to be able to actuate these facades so that it lets more of the daylight in the winter and less in the summer. So you're not having this glare problem when you're looking at your computer. So the efficiency of your building is going to interact with this device. Now, there's a whole bunch of metrics that people use, and you might see a building's LEEDs rated and all this, you know, wonderful things, and they have all these metrics. Not one of these metrics are validated. So these metrics are, you know, blah, blah, blah. So these are examples of some buildings right here in this yellow space that are LEEDs gold, LEEDs silver, LEED platinum. They are supposed to be the most energy efficient, the best buildings in the world. And they are not doing, they're actually losing their net zero quality. They're really expensive. They're not what the people intended. Again, the point I'm trying to get across is just because you say something is great, if you don't validate it and find a methodology to doing that, you're not actually going to produce something that you would expect, and it's not something that's wrong. So what we're trying to propose in our lab is to have a simulation that we can go out and validate, and this is where the ASD device is invaluable, where we can go out and spectrally validate our model to say what we're getting is what we have, see some of these buildings go through the design process, and also validate them inside to say, you know, what we're getting is what's actually happening. There's a global need for this. I'm not going to go over this too much. It's just saying that two interesting factoids I learned from working on this project is that half the buildings, high-rises that have been built in the world have been built after 9/11. So in the past 15 years, half the high-rises that existed did not exist before. There's a massive move in India and in China to move away from the rural and move into the urban environment. And this was a picture I took when I was in Shenzhen last year in China, and I just looked around. I have friends that are glaziers looking for work in America, and there are 8, 9, 10 cranes going up in Shenzhen left and right, and there's, you know, tons of buildings going up. We want to make sure that when these buildings go up that they're do have a good green quality to them, they are sustainable, and the people in them are comfortable as they go through. So when we have this design process that goes, an architect will sit down. Now we're all engineers, and you know, we have our design process. When an architect sits down, they have this idea of a conceptual design. They're going to go through a form and space. So some architect looked at this room and said, I want to have a tiered structure because the students will have a better view and nobody's head will block. So if some guy 6'4" like me sat in front of somebody short like Bill, I wouldn't be blocking his head as he's trying to look for his talk. But they do it really quickly. They spend a very small amount of time in these two steps, and they spend a large amount of time in the construction part. So they don't have a lot of time or budget to go back through their iterations when they want to make something green, when they want to do some of the simulation. So a lot of this stuff doesn't actually happen. So what we're trying to do is do quick methods that are validated that can affect early phase design, so an architect can sit down and say, well, this is letting more daylighting in, I know this is going to change the thermal properties, how, and everything can sort of happen in a streamlined effect. I'm just going to just skip over that. So my main problem with our simulations are, when you put a bad simulation model in, you're going to get bad data out. This is sort of what models currently happen. So I would contend that most architectural weather simulation models are wrong. And they're wrong in the fact that they blur over a variety of interesting details. So for example, if you have a cloudy sky, most architectural weather models would just say it's just a blurry Ithaca or Rochester sky where it's uniformly gray across the sky. Most people know that that's not what actually happens. Skies are very rich. Earlier we showed an example of some cirrus clouds where we saw they were isotropically scattered throughout the sky, and it wasn't a uniform illumination, so these assumptions are actually incorrect. They oversimplify these models of clouds, and we want to produce more interesting volumes into these weather models. And we want to make sure that they're validated in that effect. Additionally, these models do two different things. They do one thing for the visible range, and they do a whole different thing for the infrared and thermal ranges. And what we're trying to also say is why have these different inputs, why have two different models, none of them are validated, you're trying to mix and match things here. all of these are used wavelengths of light. They all use this radiative transfer. It should be one unified model that goes from doing things in the visible that moves into the infrared and are simulated all as one model interconnected. So the main thing we're trying to do is measure these all-weather skies. This is my piece of the project and the part that I spent the last 3 years on trying to do. And this is a kitchen in Ithaca, and the main thing that I'm trying to show here is that skies have a very unique impact, especially here. You see the harsh glares coming in on the kitchen. They're bouncing off the materials, bouncing all around. And over here, it's more diffuse, more shadowing, more distinct light. Adding clouds into the equation, you see it sort of goes from being really light from a clear sky to being really dark for an overhead sky. So clouds play a significant role in this illumination, but they also have this directional component associated with them where it's not just uniformly dark across the whole sky. And I can't just blur light 20% or 10% and hope to get the right answer in the end. So what we're trying to measure is basically the light on the surface of the Earth. This is something we're all familiar with, which is sort of a stock slide I have, where obviously the light is following this black body on the top. We're trying to measure it from the ground, but we're taking the ASD device and sort of pointing it up at the sky. Where in general, a lot of people are concerned with the irradiance for skylight. And that's great if you're doing outdoor scenes, yearly averages, and all that. We're primarily interested in this cone or directional component that Chip was talking about, or we're calling the radiance, such that if you have these harsh glares and light, this directional component to light is essential if you're having a building and orienting it in space in some form. So our work uses basically creates a multi-acquisition device where I capture a series of HDR images. I use a spectroradiometer. I have a irradiance sensor set up. And I create this data set that basically allows us to have a multi-tiered capture that sort of exists. To do this, I then simulate and try to fit analytical models and data-driven models to create better skies so that I can produce better data. And it allows for a robust comparison and validation so I know what I'm going to get both from the simulation model and also validating it throughout the architectural design process. So this is a series of our devices. We utilize the wonderful backpack ASD gives us as I climb up 5 ladders in various buildings of Cornell, and with all this stuff on my back and setting it up on our roof. So here we've outfitted the 1 degree 4 optics on 2 pan-tilt servo motors, such that we can scan any point in the sky dome that we actually want to. I have an HDR camera set up that gives me a fisheye of the entire sky, so I can show you those images of the skies I'm actually capturing, and a irradiance sensor so I know what the irradiance of the sky is actually sort of producing. Now, I was a postdoc. I don't have a big budget, so I do a lot of things with duct tape, and it's not as refined as Chip's model because I don't have the budget he has, but it definitely works. So we basically have outfitted our own fitting devices to actually fit the ASD device. It basically can scan any point in space that we want to. I have a compass just to ensure that the direction I'm getting is what I expect, and 2 pan-tilt servo motors to actuate the device into any angle that I want. So it basically goes throughout the sky and scans any same pattern I want to actually do, so I can scan the sky and get the 1 degree radiance component of what that light is actually happening at any given point, which is very useful to both validate the radiometric properties of existing skies and evaluate radiometric qualities of my skies. We also have taken the data and also have a data-driven model, which is sort of calling our ground truth model, which basically takes this data and actually produces a model that's not analytic, that's produced both from data. So we are using the older version of the Field Spec Pro, so probably one of the original ones, which looks like it came out in like 2001 from your guys' slide. And we designed our own component here. This is just an old sketch that I had of trying to, fitting this together in my head, and a couple design models of how to fit this such that it doesn't block anything and moves around and gets us the light and actuations that we actually need. And we control everything from our own Arduino so that we can program and do a variety of scanning patterns that I'll get to in a few slides to show how we want to measure clouds versus how we want to measure the clear sky. So looking at the sky spectral data is really interesting. Earlier you showed one example of the radiance from the sun, and we're also interested in this sort of diffuse skylight that exists. So if I take the spectral radiometer and I point it at different orientations in the sky and look at it a slice across the sky, we can see the different components of the skylight that actually exist. Now if I leave that same point and keep it for 20 samples over a 5-hour period, the light also changes. So this spatial and temporal aspect of the radiance that changes over time is what we're really interested in measuring and validating for our models, such that we can actually make sure that when you have all this light coming in, it's going to be what you expected in the building when you design it. Now, again, clouds also throw a big problem into it to make it more challenging. So the gray line shows the spectrum of solar disk that we captured. The orange is a cloud, and the blue is going to be the blue sky. Now the cloud is obviously going to be a little brighter than the blue sky because the clouds act as these big diffusers. So as the sunlight comes in, it's going to basically diffuse the light into a very large area. Not as powerful as the sun, but not as more powerful than just the blue sky. If we sample the sky and different clouds at different spots, we're also going to get different spectra, and that's also kind of interesting too to see that it's more powerful than the blue sky, but even going around, depending on how the light is reflecting off it or multiply scattering throughout it, you're going to have different properties of it throughout the entire process. So I'm going to just show you some examples of the better skies we're doing. It's not the focus of this talk, but what we do is we try to capture the sky with our device. We use this data to interpolate a whole bunch of points for the different samples that we have, and then interpolate in them to generate a data-driven sky. So once we actually have this data-driven sky, it's actually spectral across the entire hemisphere with this interpolation. So at any point, I can point into this and see what that light actually is going to give me, and then basically use that sky to basically have a daylighting model for a kitchen scene that is, I'm an engineer, so this isn't going to be as pretty as some of the architectural scenes. But it's pretty close to the kitchen we had before, where I can actually do these, harsh skylights and everything, and it's both doing a thermal model and a daylighting model all together. If I measure any point, I can sort of validate that it's actually working as well. Now, if I was to throw clouds into the mix, it's a much more challenging problem. So what we do is we go into the remote sensing community, and there's some wonderful satellites. Specifically, we're using the GOES 13 and 14 satellites to get us where they sense the cloud tops and cloud bottoms. They also give a lot of interesting information on the microphysical properties of the cloud in between to say, okay, here's what the extinction rate should be, here's the single scattering albedo, blah, 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 that we can fit into a volumetric model to create clouds. So what we do is we take our input of, we have, with the fisheye of what it should look like in this model from the GOES data of the cloud top and bottom, and we try to simulate and create a volume of what this cloud actually should be in the hemisphere. So we take this model, put it together, and we can create this volume, and then put that volume into our radiometric transfer simulation to try to get what the cloud actually should be, rather than blurring it to be one constant cloud across the entire sky. Once we get that, we actually can create accurate illumination. So this is an example of what this should actually be. So this is what we're hoping to get. This is what we actually get. It's pretty close. It's improving every time we actually get to do it. But the more important thing, if I take a point and I measure it, it follows the rough shape of what's actually happening. We're not quite there yet for getting the exact spectral match, but the spectral match is getting really, it's a lot closer than what it was, so we've taken a big step forward that way. But there's still a lot of improvement that we have to get it to be kind of exact to what is actually happening in the properties of the cloud. But given that we can only measure things on 1 kilometer scales, we're doing pretty good to match the shape and profile of our matches. Then, once we have this model, we can then use this to do daylighting and heating simulations inside the model. And then this is, again, a simulation that I recently just ran and submitted as a paper to show that we can create accurate daylighting in the previous picture model that I showed before. Here's just some matches to show visually what's actually occurring. Just to show you on top, these are photographs. On the bottom, these are our simulation models. What we want to show next is that we can take our photograph and our measured radiance and match it to our simulated model and volume to our simulated radiance. So this validation part, we basically, to validate this, take a sky model and scatter 25 points in a small region. Clouds move quickly. The ASD averages a bunch of samples. Everybody that uses the device know you're not going to get a sample like that. It takes a second or two, and if I want to take 25 samples, it's about a minute to 2 minutes, depending on how many samples I'm averaging. Clouds could move dramatically in that time, so we try to keep a small volume and a small amount of samples to actually validate what we're doing. So here's just some examples of some close-up matches. So if I take this example of some stratus clouds, point the ASD device at these 4 particular points, and look at the black measured curve averaged over 40 spectral bins. And the only reason why I'm doing that is because I'm simulating over 40 spectral bins, because the simulation takes a while to actually run. Initially, I just wanted to make sure that they're sort of accurate to show apples to apples. You can see that the general shape is being matched on what we're actually simulating to what we're actually measuring, to show that our simulations are producing ballpark ranges of what the illumination should be. We're hoping to improve this even further by adding more and more properties to our volume and our scattering methods and our radiometric transfer methods inside our clouds. But we're pretty proud of where we got to, and the fact that this is generally doing 10 times better than anything that's been done in computer graphics or architectural visualization in the past 40 years. And we're actually able to produce clouds that actually have decent spectral matches. This is more of an Ithaca sky, or a sky we'll experience today, or Rochester, or, your standard sky. And we're trying to also show, that it's not just one model. We have a whole bunch of different skies. We basically go up to the roof every time. Bill's going to lend us our device and go up and measure a lot of skies that show we sort of have this good validation. Now, just to show you an example, there's been a lot of different models proposed. Again, the red line here now is the measured data, and all these other models are going to be the variety of models that sort of have existed in space just for clear skies. And what we're sort of contending with this is that I'm sort of saying that all the models were wrong before, and we're making this big leap. This is kind of showing that all the models were all over the ballpark. Nothing was consistent, like this line is up here, and then on this angle is down here. We're trying to show that our model is consistently capturing the shape and being consistent over all the angles we're measuring, and it's a lot better than what's sort of been done in the past. Previous models, if I sort of show it on the hemisphere and average it across there, have 2 major problems. They're really bad around the horizon, and they're really bad around the sun. And it's because they just are not able to handle the radiometric properties correctly or do the radio transfer simulations with any type of particular detail. And this happens for any of the samples that we were measuring for the previous work. So in the future, what we hope to do is provide these better solar and sky dome models that we're simulating and validating it with the ASD device, and bring it into the architecture community of saying, okay, now that we have this measured long simulation model, we can create an analytical model from it and give it to you so that you can get interactive feedback in this early stage of the design process. So you can say, okay, I have a problem with my design here, or I have a problem with my daylighting design here, and I want to maybe put a dynamic facade in there or do something there for the thermal. So this is going to be great, especially as our buildings go from being stupid buildings to being smart buildings, such that you can basically think you can put maybe an actuated device in the roof of your building, a fisheye camera, and you can use it to control and predict your smart building, such that it can actually operate over time and adjust to the current conditions that are actually occurring. So this is something that we're trying to simulate now, and hopefully trying to propose to Cornell to do for one of their buildings in the future. So whether you're building a new building, like this is Gate Hall, where they put all these wonderful fins outside of it for our new Grand Computer Science building. So I asked them when I came here, I was like, oh, these fins, they must block the light or do anything, and no, they do nothing but make it worse. They actually bounce the light into the building, and it makes it partly unusable. So what we want to do is not just do things that are aesthetically pleasing. We want to make sure these panels are actually put at an angle or actuated such that it actually blocks the light. Maybe have devices up on the roof that controls this, and even if you're retrofitting a building, which is another building at Cornell we're retrofitting, allow have devices on here that can actuate the shades or the polarization of the glass based on what it's actually sensing both remotely and at the actual location. So in conclusion, what we're trying to do is take the spectral radiant measurements, and I'm a big advocate for saying that these measurements are important, that we need to validate our models such that when we know what we're simulating is what we're going to get when we design and build the building. It's great for rendering. You know, we still have applications where, you know, Pixar knocks down our door and say, oh, you're doing clouds. We want to put, you know, we fudge them in the Good Dinosaur. Can you show us what you're doing? So we can create them in kind of future movies, and that's a great application too. And we want to be able to just say that we can give this data and these illumination models to a variety of communities so they're more accurate. So if we had a better idea of what was going on with the conditions of the sky, when Chip and Bill actually do some of their remote sensing, we can sort of say, we can build you the sky that's actually occurring. Here's what we think the illumination is. You know, it might be useful to you guys to actually be able to understand what these changing sky conditions are actually happening. Because as the first talk sort of intuited, you don't have these days in Ithaca. There's no beautiful glory days in upstate New York. They're like 3 all year. And you have to be really careful to get one of them and go out and get it. We live in a cloudy sky. We live in a dirty environment, so we should be able to sense and simulate things in that environment. This is what we want to do is for sustainable design so that we can create these buildings that actually have an impact into the real world. So thank you for your time, and hopefully everybody enjoyed that talk.
Any questions? Oh wait, there's a question in the back.
Yes?
Can you go back to slide 39?
39, what? You really paid attention. Sure.
You only go out to 700. Any reason why you didn't show any of the...
Yes, okay, great question. My first and funding comes from computer graphics, so we're obsessed with the visible. So some of these graphs that I took are a lot for the visible range, but when we do all our measurements, they do both basically from 350 nanometers all the way out to 2,500, which the ASD actually does. We validated and simulated them for all these applications. However, since a lot of our funding comes from the computer graphics industry, they're just obsessed with the daylighting and visible models. It's the only reason why I'm just showing the visible graphs. I have more in a couple papers I can direct you to if you're interested in seeing what's going on. For clouds, it's really actually important and interesting. So the cloud stuff will have bumps, obviously, for the water content that Bill just talked about with his drying process. We experience the same issues with measuring clouds, with having these absorption and microphysical water properties there.
So did the other models that you compared it against also go out into that?
They do not. So that's another reason too. We don't have no comparisons as well, which is a great point.
So a lot of these models just
stop at the visible. So again, the majority of these models are just trying to do daylighting studies and visible stuff. They'll have a different model that will just do the IR stuff. And what I'm trying to say with my work, and that's my sort of big pitch as I go around to doing some of these faculty talks, is I want to have one unified model. We want to put it all together and validate it all together and not have these two great simulations.
and they're all photons.
Yeah, it's all light, it's all photons, it's all Maxwell's equations. We don't need to have all these, mishmash of stuff together. It should be one sort of simplified model. But that's a great point and a great observation. Cool.
Well, thank you, everybody. We're going to take a quick break, and there's coffee set up outside, also back in the fishbowl just to the left as you exit the auditorium, and then we will meet back here at 2:20. Thank you.